So we've actually kind of seen the chain rule before. The chain rule is a real important rule in finding derivatives in calculus. Okay, we also, it could be referred to as finding the derivative of a composite function. Composite functions are, we saw those in MHF a little bit. We've talked about them briefly, I think, in this course. Okay, and it's kind of when you take two basic functions and you start lumping them together. So we, as I said, we've already really been doing this. We just didn't call it the chain rule. We called it power of a function rule. It's the same idea, although chain rule is a little bit more general, and you could think of applying the chain rule to all kinds of functions, not just polynomial type with exponents. And so we'll see the chain rule later throughout the course. It'll take on a bit of a different look maybe, but here we go. And today actually we're going to mostly be doing something slightly different with the chain rule. But the chain rule itself is an important concept. And it goes like this. If the function h is a composite function where it's f of g at x, remember this was like f circle g. Remember that from MHF? That's just a different notation. Then the derivative of h is the derivative of f multiplied by the derivative of what's inside, so of g in this case. So again, it's going to look like the power of a function rule that we've been looking at. If we're only worrying about exponents, it's going to look familiar. In terms of function notation, let's take a look at what this over here is telling us. So h at x equals f at x, but at g. So put g inside, which is 4x squared minus 5x. Very briefly, very important. You have to make sure you're never making this mistake. I have seen it in the course. So like I have seen people do this once or twice. You cannot take an exponent and apply it to two parts in a bracket that are being added together. Cannot. Never do that. Somehow force yourself to make sure you're never doing that. If I have this, that is a to the n times b to the n. If I'm multiplying in the bracket, I can do that with the exponent. That's what we were talking about. But not if you're adding. Oh my gosh, not if you're adding, right? We talked about this a lot. Starting in grade 10, it's a big deal. So be very careful of that. So h prime is like the derivative of f at x. So that's 3 take the exponent out front and just the same thing in the brackets, and then subtract 1 from the exponent, nx to the n minus 1. But then the other part is times the derivative of g, right? So the derivative of g, this is the derivative of what's inside the bracket. So multiply by the derivative of what's inside. So this is 8x minus 5. So notice it's like f prime of g at x. The g at x inside the brackets is the same, right? And then that's g prime. So again, familiar, but there's a slightly more general form called the chain rule. And I think of it as, we've got all these skills like the product rule and the quotient rule and different ways of finding derivatives, and we can chain them together to get derivatives of larger, more complex functions by chaining the stages of taking a derivative together. Does that make sense? I think that's why they call it the chain rule. All right. That being said, we're going to, like as I mentioned previously, we're going to do some sort of different kinds of problems with it. This is a type of question where it gives us some values of functions and doesn't actually all the way tell us what the functions are. But we can start to make sense of this and plug in values. You kind of have to make sense of it for yourself, but you plug in the values when you can. And then there will be another kind of question that we're going to do that takes a different approach on the chain rule. It's really useful. So determine h prime at 4. So I'm going to start with h. Where am I going to do this? I just want to make sure h at x equals f at g at x. So h prime at x, just using the chain rule, is f prime of g at x times g prime of x, right? That's just chain rule. That's just literally what was on the last page. And now it wants us to determine h prime at 4. And it might look a little bit weird because I haven't actually done anything, like we're not actually even talking about a function, we're just talking about general function notation so far. But I can still do it. Function notation says I take whatever I put in these brackets, I replace x everywhere, right? So whoops, not x anymore, 4. Okay with this? So can anybody tell me anything that's useful now so I can go further with this? Hello? Okay, perfect. So this, you're saying this right here is -2, right? It gave us that value. So I can go equals f prime at -2. And then you said, same thing, this, it gave me the value of there. So this is just equal to 1. So what are we missing? Do we know f prime at -2? We do not. But what do we have? Fu. Oh, sorry. We have the function f. And so we can find the derivative of that. So I'm gonna let pause there and let you try that. Okay, so now I've got that. Exactly how it's simplified doesn't really matter at this point, because what I'm going to do is find f prime at -2, right? That's what we wanted. So I could see all these questions kind of being like slightly different, like it's like they're a little bit of a puzzle, you know what I mean? So it's going to give you, happen to give us f in this case, maybe another time it gave us g or something like that, right? So every question could be a little bit different, and you have to put the puzzle pieces together. But it'll be things like, if it gives you a function, you're probably going to find the derivative of that function and then use that for something. So this is 4 plus 12 over 25, or 16 over 25. So then back over here, which equals 16 over 25 times 1, which is just 16 over 25. Any questions? Yeah. Mm-hmm. Here, yeah. It better not affect the way our answer turns out, because algebra shouldn't change our answer. So I don't think so, because you'd still have the u. The u can't disappear. So I think you'll get the same thing. Just the computation will look a little bit different, right? You don't look quite satisfied with that. -2 minus 6. I'm writing 5, right? And then the bottom's going to be the same, so the bottom's going to work out to 25, and that's going to be -2 times -8, so 16 still. This should work out. Are we good? All right. Next question. There is another way you can do that. We're not going to go over it right now because it's not super important, but it's kind of interesting, so I'll either post it or maybe show you under the document camera after. Just kind of an interesting, different way of looking at it, I guess, gets you to the same place. Okay, so here is a new look at chain rule. This is another way that we can solve chain rule questions. This is kind of, again, using the Leibniz notation. We've talked about that a little bit, right? We've seen the dy by dx. So, but this one's interesting in that it's a different way of looking at it, and maybe if you're given the question in such a way where I'm given y in terms of u, and then I'm given u in terms of x, that we can chain the derivatives together to find the overall derivative. Hopefully that'll make more sense after we've seen an example of that. I'll let you get that copied down. You could take, like the original function that we saw on the first page that we just used as an example to demonstrate the chain rule. It wasn't presented this way, but you could backtrack and put it in this form, right? So all this is saying, if u equals g at x, then f at u means f at g at x, right? It's the same thing, composite function. It's the same idea as what we saw above. So you could rewrite any question in this form if you wanted. And what it tells us is if I take the derivative of y in terms of u. I'm going to talk about that a little bit more in a moment. And then take the derivative of u in terms of x. I can multiply them and I'll get the overall derivative of, y in terms of x. Okay, so let's get started and see exactly what this looks like. We're going to do a couple of these. First thing I want to do is it gives me x, but you're gonna notice later on I also will need the value of u at 4, so we're going to do that. So if x equals 4, I can sub that in for x and find the corresponding value for u. So 2 times 2 is 4. So in this case, u is also 4. That's just a coincidence. And you probably wouldn't show this in 2 steps, but just for clarity, we can do this. So I'm going to find dy by du. And so that's coming from here, right? So that's 3u squared minus 2. And I'm going to find du by dx. Don't get caught up too much in the notation. Don't get bogged down in that. It is just notation. Now, on Thursday, we're going to look deeper at exactly what this dy by du means. But for today, at least, you can kind of just think the thing that's on top was the thing on the left, and the thing on the bottom was the thing over there on the right. You know what I mean? Like the y and the x that we're used to. You can kind of just think about it like that for now, I think. Okay, and this one is, this was 2x to the 1/2. So when I bring the 1/2 over, multiply by 2, I get 1. So du by dx is x to the negative 1/2. Or 1 over the square root of x. Okay, and dy by dx equals dy by du times du by dx. Three u squared minus 2 times 1 over the square root of x. And then the question actually asked us to find dy by dx when x equals 4. And so now you see that this is why I needed the value for u as well, because my equation here has a u and an x in it. So that's 48 minus 2 is 46 on top over 2, which is 23. Any questions about that? So it could be, I mean, I think it can be a little bit confusing just trying to figure out what variable relates to what, like where the variables fit in. And it's not always going to be y and u and x. But if I look here and I see that this was y and u, and I had, dy by du, and this was u and x, and I had du by dx, like that's kind of how you're going to make sense of it, right? Questions, questions, questions. All right, I think we have one more. Oh, this one's got 3. Okay, so put your pencil down and watch. Maybe this will be a good way to look at it. The first one is y in terms of u. Y equals something to do with u. So from that, I can get dy by du. The next one is u in terms of v. So I can get du by dv. And you can see how, like these kind of, like if you think of them as fractions, those cancel, right? Like that's kind of what's going on. And then I have v in terms of x, so dv by dx, and I end up with dy by dx equals all of that. Do you see how that works? You're chaining them together. And so I find the derivative of each of those, multiply them together, sub in at x equals 2, and I've got my value. If x equals 2, v equals 2 squared plus 1, which is 5. And u equals 5 over v, so 5 over 5, which is 1. So v equals 5 and u equals 1. I need all 3 of those values. This does the same thing as the chain rule before. I mean, if you examine the two of them and think about it, you'll see that it's doing the same thing. The difference is I'm got more variables doing it this way. The last way was everything was in terms of x. And this way I've got u and v and x, and all of those are my final answer, and then I just need the values for each of those, which we can find, and we can sub it and solve. So dy by du is the derivative of y. So that's 6u squared minus 8u. That was the derivative there, right? dy by du. Times du by dv. That's this derivative. And if you look at this as the quotient rule, there's different ways that you could look at this. You could take the v from the bottom and put it in the top, or you could look at it as the quotient rule. However you want to do it. It works out to negative 5 over v squared. So if it was like 5v to the negative 1, that's probably the easiest way. Multiply by negative 1, v to the negative 2, right? And then dv by dx is 2x. So when x equals 2, v equals 5, and u equals 1, just sub in. That's it. Yep. Yeah. Yes. I think sometimes you also might just say it's awkward. That's a problem with this notation. It's not nice. Like, although if we were using function notation, it wouldn't work with the three different variables anyway. It's a bit awkward, but it's a notation that you use to say like I am evaluating this derivative at these values. Yeah. Um, I think we also did it like where you literally write at x equals, so you could do that too, but you could do this one. Well, any other questions? Are we sure? Let's see, there's a practice.